All right, so in this video, we're going to be talking about the Quarter 3 exam review for Algebra. We're going to be going over the first assignment, which covers numbers 1 through 6. If you don't have a specific question on 1, you can skip ahead to 2, 3, 4, 5, 6. The time codes are in the description as well as in the timeline of this video. All right, so let's start with number 1. Minneapolis, Minnesota, and Portland, Oregon have very similar latitudes, and latitude measures how far north or south a place is, which in turn affects the temperature. The histograms below show the daily high temperatures in degrees Celsius that were recorded during July of 2013 in each city. Which pieces of information can be gathered from these histograms? So we have two options, well, three options really, but first option is it was warmer in Minneapolis every day. Second option is Minneapolis had the coldest daily high temperature of these two cities. And C, none of the above. So we have to confirm or deny that these are true statements. So let's do A first. It was warmer in Minneapolis every day. Well, we have Minneapolis right here. Now, with histograms aren't very specific. Histograms are very vague in what they tell people. So in this case, we know that we're told the temperature, and we're told how many days a specific city has that temperature. But that temperature, how it's recorded, can be between certain other temperatures. So for example, in Minneapolis, we know there was at least one day that had a temperature between 15 and 18 degrees. Does that mean it was 15 degrees? Was it 17 degrees, 18 degrees? We don't know. We just know it was in between these two temperatures. So are we able to tell that it was warmer in Minneapolis every day? Well, if we look at Portland's and compare it to Minneapolis's, well, we notice that Portland has the same kind of scale for temperature. 21 to 24, we got 21 to 24 over here, 24 to 27, same here. Yeah, they're basically having the same scale. So can we determine if Minneapolis had a warmer temperature every single day? Well, no. It doesn't tell us the specific days. It doesn't say, oh, Tuesday the 12th, it was this degree in Minneapolis and this degree in Portland. It doesn't tell us that. It just tells us the daily temperature, the average temperature. So we can't determine if it was warmer every single day in Minneapolis. So we have to eliminate that possibility. The second option we have, Minneapolis had the coldest daily high temperature of these two cities. Okay, well, again, we're looking at Minneapolis, had the coldest daily high temperature of these two cities. So again, it's not asking for a specific day. It's not asking for did it happen every day. It's asking did it have a cold daily temperature and the coldest compared to Portland. Well, let's look at both of their coldest temperatures. In Minneapolis, we had 15 to 18 degrees. Again, not specific. But if we look over here, we noticed Portland doesn't even have a temperature between 15 and 18 degrees or between 18 and 21 degrees. Its coldest temperature is somewhere between 21 and 24 degrees. So does Minneapolis have the coldest daily high temperature recorded? It does, right here. So we can agree B is our answer for that. All right, if we move on to number 2, talking about macaws. Again, we're staying with stats. Macaws are tropical birds that can live a very long time. The box plots below show the lifespans in years of a random sample of macaws that lived in captivity and a random sample in the wild. So it's asking about the center and the spread of each of the box plots. So the center of the captivity versus the center of the wild distribution. And we can determine what is the center of each of these box plots by looking at the lines in the centers of the boxes. Those indicate either the mean or the median, depending on the distribution. So if we look at the centers, the center of the captivity is somewhere around 76, whereas a wild distribution, that center is, I'd say 54. So comparing 76 to 54, the captivity center would be greater than the wild. If we're looking at the spread, we have to look at the whiskers of the box and whisker plots. How far away are the whiskers compared to each other? So we have very, very big whiskers here and very, very tiny whiskers here. The higher the whisker, the less spread there is. So captivity spread, decent, but compared to the wilds, it's very, very small. So the spread of the captivity distribution is less than the wilds distribution. Again, just looking at the whiskers, you can tell that. This is a very big spread, very wide spread. This is a very narrow spread. All right, moving on to number 3. There it is. Ben is concerned that he is not reading enough. He decides to record how many pages he reads each day in the month of April and then in the month of June. And he plots his data in 2 box plots for each month. So we're comparing again. We're comparing box plots of April and June. Both of these months, by the way, have 30 days. Keep that in mind. So in what month were there 15 days that Ben read between 25 and 35 pages? Okay, 15 days. So if each month has 30 days, 15 of those 30 days, so half the days were spent reading between 25 and 35 pages. So what accounts for half of our data? Well, the easiest way to look at that is the box itself. This box, remember, the left-hand side represents quarter 1. The right-hand side represents quarter 3. And the middle, or the median, or the mean, depending on the distribution, represents Q2. Between the first and second quartile, well, quartile means quarter, so we have a quarter of our data right here. And between the second and the third, we have another quarter of our data. A quarter and a quarter make a half. So in these 2 boxes, we can determine where half of our data is. That's the simplest way to look at it. So we notice half of our data is in between 25 and 35 here and 15 and 35 here. So we can assume that in April, 15 days were spent reading between 25 and 35 pages. April. The next one, in what month did Ben take a day off from reading? Well, if you take a day off from reading, are you reading any pages? No, you're not going to read any pages if you take a day off. So, which of these has a data value of 0? Well, the lowest thing they have here in April is 10. The lowest number of pages here would be 0. So we would assume June is the month Ben took a day off of reading. Now, in some of the keys, you may have noticed that one of these, or it was either April or June. That was a misprint. This is the actual answer. We have April as our first answer and June as our second answer, if you guys were wondering. Just want to make sure. Okay, so number 4. Number 4, still talking about stats. This whole thing is about stats, so we got to keep talking about stats. A chocolate company makes dark chocolate bars. The quality control department has found that the weights in chocolate bars follow a normal distribution. So a normal distribution, if you were to graph it, it would look something like this. It would have like a normal bell curve. It'd be symmetrical. This might not be as symmetrical as it can be, but this is what we talk about when we say normal. See a nice little bell curve. So it has a mean of 85 grams, and in normal distributions, the mean is that middle, denoted by mu. So that is going to be 85. And standard deviation of 1.2 grams. So we have a standard deviation, sigma, of 1.2. Okay. To ensure a consistent product, company has a policy rejecting any chocolate bars less than 82.6 grams or more than 87.4 grams. And so the question is asking what percent of chocolate bars are rejected. So what percent of the chocolate bars are less than 82.6 grams or more than 87.4 grams? To find that out, we have to use our standard deviation, and we have to go out each standard deviation until we get to these 2 points. Now this follows what we call the, I'm blanking on the rule. Oh. So 68%, 95%, and 99.7%. So every time you go out one standard deviation, you're going to have 68% of your data. If you got 2 standard deviations, you encompass 95% of your data. And if you go out 3 standard deviations from the middle of your data, and when I say go out, I mean you're going to the left one and you're going to the right one standard deviation, you will pick up 99.7% of your data. So what that means is if we go out 1 standard deviation, so if we go 1.2 to the right, we have to add 1.2 to 85, so that would be 86.2. And we have to subtract 1.2 from 85, and that'll get us 83.8. And that is 1 standard deviation. So in between here and here, we have 68% of our data. If we got another standard deviation, another one, from here and here, so we're adding 1.2 over here, so 87.4. We take away 1.2 from 83.8, so that'd be 82.6. 2 standard deviations have gone out. That means we have 95% of our data. Okay, so you can kind of see where this is going. Actually, we're going to stop right there because we have 82.6, 82.6, 87.4, 87.4. There we go. We have our 2 points that we were looking for. So we're looking and trying to find out everything below 82.6 and above 87.4 we're rejecting. But how much is that? Well, if we have 100% of our product, this whole entire distribution will be filled out. But between these 2 points, 82.6 and 87.4, we only have 95% that will be accepted chocolate bars. The rest are going to be rejected. So from 95%, what is there left to get? What is there left to find? Well, if we're going from 95 to 100%, we're missing 5%. That means we're going to be rejecting 5%. 5, same kind of rule, that 68, 95, 99.7 rule. So the shoe size of females in the US follows a normal distribution. Again, we're dealing with normal distribution. The mean shoe size is 8.5. So in the middle here, that is our mean of, what was that? 8.5. So 8.5 here at point D. All right. The standard deviation, again, we're talking about standard deviation, is 1.5. So we have to consider the graph and figure out which of the statements are true. Now, we can do the same thing we did last time. We know the standard deviation. We know the mean. So we can work from the center and go out. This is called the empirical rule when we do this with the standard deviation. So if we go out 1 standard deviation, so we go from D to E and D to C, we're moving 1.5. So adding 1.5 to 8.5 would give us 10. Subtracting it would give us 7. Again, that would only give us 68% of our data. If we go from C to B and E to F, we're moving another standard deviation. Between those 2 points, according to the empirical rule, we would have 95% of our data. So we're going from 10 to 11.5. Again, we're adding 1.5 to standard deviation. We're going to subtract the standard deviation from this side, so it would be 5.5. And if we did it one more time, A and G, that's the third and final standard deviation we're going to go out. This is going to encompass 99.7% of our data. So we almost have 100% once we go at 3 standard deviations, but we're not there yet. All right, so let's go through point by point. So point C represents a shoe size of 6. Well, if we filled this out already, we can go to point C and see if that's true. So we have it at C, and we know since we went 1 standard deviation out, We subtract 1.5 from 8.5, we should get 7. So C does not represent a shoe size of 6, so I'm not going to select that. Point D represents the mean shoe size of 8.5. Well, D was in the middle, therefore D will be my mean. I agree with that. Approximately 0.15% of females wear a shoe size 4 or smaller. Well, where is 4 or smaller? Well, if we take away the standard deviation from here, if we're going out one more, this would be 4, and this would be 13. We forgot to fill those in, but that's okay. We now know point A has the shoe size of 4. So 0.15% of females wear a shoe size 4 or smaller. Is that going to be true? Well, we know at A, it defines the boundary, the third standard deviation. So from A to G, we know we have 99.7% of our data. So everything outside of A and outside of G represents the remaining 0.3% of our data to get to 100. We always want to get to 100%. So the remaining is 0.3% on both sides. But I only care about this side. I only care about shoe sizes 4 or smaller. Okay, well, if both sides represent 0.3%, and I'm only looking at half, what is half of 0.3? Well, that is going to be 0.15%. So I agree with that. Approximately 68% of females in the US wear a shoe size between 5.5 and 11.5. Okay, well, 5.5 is right here. 11.5 is right here. So between B and F, 95%. Bigger than 68%, so we're not going to select that. Approximately 81.5% of females in the US wear a shoe size between 5.5 and 10. Now, the empirical rule doesn't give us 81.5%. So we're going to have to do a little bit of math to figure that out. So between 5.5, which is at B, and 10, which is at E, what do we know? Well, I know between C and E, that's 68% of my data. So I have 68% of my data here. Plus what? So I know C, between C and E, I just need between B and C now. Well, okay, I have to compare. From C and E, I have 68%. From B to F, I know that percent. I know it's 95%. So what's the difference between 95% and 68%? 95 minus 68. That is going to be 27%. So I know that between B and C and E and F, that extra space is totaling 27%. Now, since I only want between B and C, again, that's half of what we just calculated, so I have to divide that by 2. If I divide that by 2, I'm going to get 13.5%. So I'll add that over here, 13.5% plus 68%. That is going to equal 81.5%. So yeah, approximately 81.5% of females wear between 5.5 and 10 in shoe size. So I agree with that. The last one, based on the distribution, a shoe store should order about 95% of shoes for females in sizes between 5.5 and 11.5. Okay, let's look at the chart. Well, 95%, I know that is going to be my second standard deviation. So I go out 1 and 2. So between B and F, which is 5.5 and 11.5, 5.5, 11.5, that works out. Boom. All right, the last one, number 6. The table shows a relationship between the values of x and y. Which of the following equations describes the relationship? So, because we have a table built for us, giving us x values and y values, but there is no rule. There is no equation telling us how we got from x to y. So, best way to figure this out is just plug it in. So, if we're given 1 for x, if we plug it into this equation, that is y equals 3 times 1, which is 3. That works out. Okay. Well, if I give you 2, so 3 times 2, well, that gives us 6. That gives us 6. Okay, so far so good. And then 3, so x equals 3, so plug in 3 for x. 3 times 3 is 9. Did we give it 9? No, that's supposed to be 11. So we know that's not going to work. Okay, so we move on. So that was A. Try out B. So if I go to B, y equals 5 times x, so the first x is 1, so 5 times 1 minus 2. Well, 5 times 1 is 5, minus 2 is 3. So that works out. If I go to my next x2, so 5 times 2 minus 2. 5 times 2 is 10. 10 minus 2 is 8. That doesn't work out. It's supposed to be 6. All right, so it's not B. If I go to C, y equals x squared plus 2. So if I plug in my x's, my first x is 1 squared plus 2. That's 3. If I plug in 2 squared plus 2, 2 squared is 4. 4 plus 2 is 6. That works out. If I plug in 3, 3 squared is 9, plus 2 is 11. That works out. Don't stop, though, because 4 and 5 might not work out. So 4 squared is 16, plus 2 is 18. Okay, so far so good. Last one, if this works out, this is going to be our one. 5 squared is 25, plus 2 is 27. That works out. C works out, so we're going to choose C. If you're not sure, you're a little skeptical, we can try out D. So let's try D out. Y equals x cubed, so x to the power of 3. Plug in 1, 1 to the power of 3 is just 1. That doesn't work out automatically, so we know it's on D. All right, so that is the end of the first homework set for the quarter 3 exam review. Stay tuned for the next video going over the second assignment.